All right, liftoff and the clock has started. Yes, sir, reading you loud and clear.
Now, our final guests today are Jason Kruzan, Director of NASA's Advanced Exploration Systems Division, and Robert Bigelo, President of Bigelo Aerospace. But first, let's take a closer look at the beam, the Bigelo Expandable Activity Module.
NASA is developing the capabilities to send people into deep space. To accomplish this, we need to extend our knowledge of how to operate in space. NASA is developing habitation systems that provide safe and sustainable space-based living quarters, workspaces, and laboratories. Expandable habitats are one option. These potentially weigh less and occupy less volume on a rocket while allowing for additional space for living and working. However, testing needs to be done on the design performance of expandable habitats. The Bigelo Expandable Activity Module, or BEAM, developed under contract with Bigelo Aerospace, provides a test platform for demonstrating the thermal, structural, radiation performance, mechanical durability, and long-term leak performance of expandable habitats. The beam will be transported to the International Space Station inside the SpaceX Dragon supply vehicle's trunk. Once Dragon is berthed to the space station, flight controllers at Mission Control in Houston, Texas will maneuver the station's robotic arm to extract beam and attach it to the rear port on the Tranquility mode. After all preparations are complete, crew members will begin inflating the structure. This will be the first time an expandable habitat has been deployed on station, so the procedure will take place slowly to closely observe the expansion process and maintain the safety of the crew and the station. During this time, beam will expand from its packed dimensions of 5.7 feet long and just under 7.75 feet in diameter to its pressurized dimensions of 12 feet long and 10.5 feet in diameter. Once beam is fully expanded, the crew will pressurize it and test it for leaks. After this, beam's pressure will be equalized with the station pressure, and the crew will enter the beam and install sensors. The ground-monitored sensors will autonomously collect thermal, impact, and radiation data throughout the 2-year on-orbit life of beam. These experiments will help determine whether expandable structures will provide a viable, lightweight option for future space habitats.
Jason, Mr. Bigelo, thank you both for joining me today. If you don't mind, can we start with one clarification? Inflatable versus expandable. Is there a difference?
So yeah, we get this question quite often, both on the NASA side and on the Bigelo side, and it is good to differentiate between the two. The simple answer is inflatables make you think of things like balloons and those kind of things that don't have a structure in and of themselves. You inflate them, it loses air pressure, and it instantly collapses down. An expandable structure is more like a tent. You think about in a pack configuration, it fits neatly in your car and in your backpack. When you go to a site, you set it up. You can open the windows. You can get in it, get out of it. It keeps its structure at that point in time. So we tend to call things of this nature expandable because of that kind of the rigidity of the device. If something were to happen, it actually still maintains its physical structure even after even reduced air pressure that they have as well. So, with that kind of initial question out there, I'm going to touch on 3 different things. First is, why do we need habitation? Which may seem like an obvious question. The second, talking about the potential use of expandables, and then a little bit about our demonstration that we're doing on board with this flight experiment. First off, habitation. So as we send crews off to faraway distances like Mars, you heard mention of other folks on the panel here talking about mission classes of up to 1,000 days, 1,100 days. With that, we need a place to live. We need a place for logistics. A round trip to Mars may take us up to 300 cubic meters in storage volume for both the live-in and all the goods that we have. So we need a very large habitat to live in. Why expandables? So today, everything we've ever flown has been metallic structures. We have a wide understanding of metallic structures, but there are limitations to metallic structures in that the largest thing you could ever fly is what fits in the rocket's fairing. It's never going to get any bigger than what you have in the fairing size. And again, getting back to that 300 cubic meter size volume that you want. So we've always considered expandables. That's why NASA did the original investment in Transhab. But we had never actually gone all the way to flight. So with the beam module that we're flying here, we're actually flying a higher factor of safety on that because of our unknown knowledge about expandable structures. But specifically, we want to understand the structural integrity, the radiation performance of these, and the temperature controls of beam in order to actually help inform our choices for deep space habitats. So we're going to do that over these 2 years. So with that, I'll turn it over to Bob to actually talk about how did they actually build this module.
All right, so as Jason says, our heritage is from the NASA TransHab program, and we became enamored and enchanted with that architecture and saw its potential. And so if I could go ask for the first slide, please. That's our home base in North Las Vegas, Nevada. It's situated on 50 acres. There's 365,000 square feet of manufacturing and fabrication and design space at that facility, and that's where everything is made. We function as a general contractor. About 50% of all the hardware that goes into any of our spacecraft is created there, and we subcontract out for other hardware systems from other companies. So we don't make everything. It's about a 50-50 kind of balance. Next slide, please. And that represents the beam before it was sequestered in the trunk of the Dragon. And as you can see there, it's not terribly large, kind of a layer cake sort of fashion. It is a different shape than we were used to. We flew 2 prior missions, Genesis 1 and Genesis 2, thanks to the Russians in 06 and 07. And those had to be configured to the shape of a fairing. This had to be configured to the shape of something much different, half the size of, or half the shape maybe of a soup can. And so we had to come up with a way that was practical to orchestrate that, to fit in that enclosure. So it suggests that you may have other kinds of challenging enclosures, potentially, that you could still adapt to expandable systems. Next slide, please. This shows it going into the trunk of the Dragon. Next slide, please. And of course, there's the Dragon in the trunk itself, and as you can see, the configuration of that. Next slide, please. There's the beam by itself showing the docking adapter system, and the little kind of antenna-looking thing on the end is what the Canada arm is going to grab onto to be able to secure itself to the beam and remove it from the trunk, and then put it onto node 3 for berthing. Next slide. That's a perspective of size. Roughly a 6-foot-tall person adjacent to the beam. Next slide. That's a transparent system or portrayal of what the interior looks like. It's quite empty, as you can see. And the thing I want to impress here is that the beam is an experimental spacecraft. It has this type of architecture has never been flown before. It has been bound up for over a year, waiting for launch. We're not 100% sure of its behavior. It is a testing station. That is the whole point here, in all respects, not only in monitoring what is the environment inside going to be like, and radiation exposure and defense against certain kinds of things, perhaps debris, maybe, or certainly radiation and temperatures, but it also potentially may even someday NASA might give permission for some kind of a commercial application to be operated inside. We don't know yet. So it is a testing facility. It's human-rated. There will be people inside periodically. So it has its unique spacecraft. Next slide, please. And this slide shows it's being attached to node 3. So you can see the size is quite a bit smaller than the node 3 itself. It's the beam is 16 cubic meters, as opposed to our B330, which is 20 times larger, 330 cubic meters. Next slide, please. And that shows where we hope to have, by 2020, 2 330s ready for launch. This shows them with a CST-100 on one end and a Dragon on the other end, so we are sort of politically correct there. And anyway, that represents 660 cubic meters of volume just with those 2 habitats together. And that's what we hope to deploy sometime around 2020.
Thank you, gentlemen. We'll go to questions in a moment. As a reminder, if you're in the room, please raise your hand to ask a question. If you're on the phone line, please press *1 to enter the queue. And if you're following us online, use the hashtag AskNASA. Now, first I'm going to invoke my moderator privileges, and we have two models up here. I was hoping, Mr. Bigelo, can you explain what we're looking at?
Sure. Of course, this is the beam structure here that we have, and this is a 330. The 330, as opposed to the beam, is intended to not rely on any other spacecraft for sustaining life. It is essentially a standalone space station in and of itself. Contrary to the beam, requires complete assistance. It is an enclosure, but it's lacking avionic systems, propulsion systems, ECLS systems, so it is much different than the much larger system is.
Great. Thank you. Any questions from the room? We'll start here in the second row.
Thanks, James Dean Florida today. Mr. Bigelo, how important has been to achieving your 2020 hope for launching a private station? Is this mission essential to creating the confidence for customers to sign up for a station like that, to signing launch contracts, or is it more about showing NASA that this is a deep space technology?
Yes, all of that. No, seriously, it is an important step to us. It really is. That NASA has the confidence in our little company to be able to do this. We are very proud to be able to actually get to a point of deployment on a type of architecture that was begun in the 90s. Although expandable systems go way back, decades before that, still in the 90s it really got serious because NASA at that time was looking for enclosures that were safe and large to take people to Mars, in theory. So it's kind of come full circle now. So we're excited about this opportunity. We do hope that it does lead to other extensions of relationship, that we have with NASA.
I'm sorry, just a quick follow-up. 2020, are you talking about a private station for some customer other than NASA, or is that something NASA would be participating in as well?
We're working on a combination of things.
Dan Billow from Channel 2. For Mr. Bigelo, you talked about generically some commercial applications. What do you mean? What are your dreams? What could result here? What kind of commercial applications?
Well, our business model is essentially, my background is in development and construction and general contracting and banking and everything to do with real estate. So I transfer a lot of the business case from that industry, and essentially the foundation of our business case is time sharing time and volume, and branding, which includes anything from naming rights to all kinds of advertising or whatever, the kind of thing that you would see perhaps in the case of income streams in universities. You have naming rights for lecture halls and wings of buildings and the building itself, and then eventually the college. And so all that's applicable to structures in space that are commercially operated. We would operate these on behalf of nations who have astronaut corps and others that aspire to have them. And right now, the frequency of opportunity to fly is not often. Other than for the United States and Russia, it's about once every 3 years, close to that. And some countries maybe never, or very, very seldom. So there is a substantial appetite out there, we've discovered, and so we think that's a market. The corporate world, like Lilly, for example, certainly is any material science, organic or inorganic, is absolutely mainstream in our thinking, that we would very much want to host those folks. So it's a combination of everything from what you could manufacture a product-wise and send down. It could be information you're sending down, not just a hard piece of material of some sort. It could be national image. It can change an image of a country overnight to have that kind of facility, or to induce Lilly to locate their plant in their country and offer them that kind of a resource in orbit as a very unique laboratory. And naturally, NASA could be a very important customer to that kind of an industry, and help to save NASA money and be able to spend money for just discrete periods of time and a certain amount of volume that is really what it needs. Not having to write a much larger check to buy the entire thing. Why do that? So our model is trying to propagate the opportunities among the largest groups of folks we possibly can for the lowest nominal cost that we can.
Hi, can you explain how exactly the beam will be expanded, whether it be via pressure or mechanical or some combination of the two?
Yeah, so after the beam is birthed to the space station, the initial pressurization of it will be handled through what we call the intermodular fans, IMV fans. These are precision fans that move actually air between modules on board the ISS. So within Node 3, there's IMV fans that will actually flow air into the beam module. That'll get it up. It'll allow it a very controlled expansion of it, because we don't actually know which way it'll expand. Our models say one thing, but models are models. So we want to actually very slowly and carefully start that initial inflation. And then once we get up to a nominal pressure, then we'll actually open up the tanks that are inside of beam and bring it up to the full station pressure. Beam is carrying enough replacement gas to basically inflate itself. So we'll make up the gas back to station after we finish the inflation sequence. So it's gas neutral for its entire expansion.
Thank you. We'll go all the way to the back.
Thanks very much. Reuters, I have a few different questions. First, for Mr. Bigelo, after launch, what in your mind is going to be kind of the most critical parts of the mission? And are there any contingencies if there is some issue with it unfolding or something else where the whole module could be jettisoned? In other words, what kind of plans do you have for that? Let me start with that. Thanks.
Well, I think my personal opinion is my focus on seals. Whether it's a submarine or anything that is an extreme environment, you want to be able to protect that enclosure. So whether it's, in this case we don't have windows, but whether it's in our B330 we have 4. So whether it's hatches and bulkheads or windows, my first focus is on the successful functioning of all of the seal mechanisms. No, so I'm not worried about the hull. I'm not worried about anything to do with that. I'm worried about the interface between metallic systems and soft goods systems. It's a very complex interface. So that would be my first concern. If I were a drinking fellow, my first concern might be going to the nearest tavern. You know, right after lunch saying, thank goodness that, you know, it passed that. But I'm not, so.
And then your second part of your question on contingencies. So yeah, there are contingencies on the outside of, in most extreme case, we have the ability to potentially go out and even conduct an EVA to help with the assistance of removing strapping and those kind of things on the outside. We have multiple ways to inflate. As I said, we're using the IMV fans. We could also use the compressed gas that's in the inside as well. And in the most extreme case, if none of the options worked, we can jettison the module by using the robotic arm. But we don't envision that. That's plan F, several down the the scale.
And are you inflating with just air, regular air? And as far as the future beams, or would the $17.8 million roughly that I think NASA is paying for this, Mr. Bigelo, is that actually what you think these things will cost, or was that a special demonstration discount that NASA got?
I agreed for a long time with that low figure, believe me. So, you know, it's, no, that was a unique situation. You know, as I mentioned before, our business case is to sell discrete periods of time and volume. So this was a very unique situation for us and for NASA, and we did try to accommodate NASA the best we could.
Yeah, and on the air question, it is kind of our, obviously the station air was standard station air. The air mix that's in the tanks is up to the same quality of air mixes that we fly on normal missions as well. So it just happened to be sourced from Nevada, though. So.
Yeah. I understand the reduced volume of launching a collapsed module like this. That's an obvious advantage. Can you talk a little bit about the relative the balance between not only the size but also the weight of the module compared to a typical hard body module? So those advantages, weight and size. Thanks.
Yeah, the advantage is tremendous, not just in volume but in mass as well, because per cubic meter. And that's how you equate it, right? So most of the modules on the ISS do not exceed 110 cubic meters. I think that's the largest that's probably on the ISS. So you're getting 3 times that per launch. You know, and our mass happens to be around 43,500 pounds, and so that's a huge benefit.
Yeah, this is one of those things that it depends on the size. So something like beam was not optimized for mass. And in fact, it has a 4 times factor of safety, where our standard metallic modules are 1.5 to 2 times factor of safety. So we actually have gone overboard on protection and those kind of things because of our unknown performance of the vehicle. So as things scale, so if you had something like a Cygnus, which is relatively close in size, mass to volume performance is about the same. However, that's with the extra factors of safety, and you can't really compare those two apples to apples. But as you scale up to larger sizes, as Mr. Bigelo stated, that's where the advantages of soft goods really come in from a mass performance. The strength and material performance as well, if you look at metallics versus soft good performance, it's almost an order of magnitude from a material mass strength property. So there's a reason why bulletproof vests are made out of soft goods, not rigid materials, and it's a strength of materials and stopping power for that. And so you're really taking advantage of the material properties inherent in soft goods as well.
Thank you all. I believe we have some questions from online, so we'll take one for social.
Yeah, from social media we have a question from John Ship. He's asking, does the material composition of beam pose any potential detriment to the overall solidity of the ISS as a pressurized habitat?
No. It's a simple answer. The external cloth on the beam is a beta cloth, which we use commonly on the outside, and all the other rest of the materials went through extensive testing for outgassing and such, and went through our standard approval processes.
And from Sophia, we have a question. Has Bigelo used any 3D printing of parts or components for beam, or do you plan to?
No, we have not, but we do expect that that's going to be a very valuable component to future spacecraft.
Right here.
Josh Dinner with the Orbital Space. The beam is essentially made of cloth. And I imagine that is going to be a lot more absorbing of sound, of the ambient noises created by the station. And crews are scheduled to go in, I think, 3 to 4 times a year. Are they allowed to go in if they want some peace and quiet, for instance, other times?
Yeah, so our nominal ingress strategy is about 3 to 4 times a year, primarily to retrieve data. We have data storage devices and those kind of things that are not hard plumbed into the ISS, so we need to go in and get the drives out and download that data. After a period of time, we really do want a quiescent period of time towards the beginning of the experiment to kind of get nominal data of its performance. In theory, we should be able to get that in about a 6 months time frame. There's nothing that restricts the crew from going in more often. It will be a relatively quiet area, but at the same time, we do air exchange inside of the beam. So it's not as quiet as you're thinking, because there's still air movement that's occurring in there, but relative to the rest of the station, absolutely, it'll be much more quiet. And there's no restrictions of them going in.
Thinking ahead, do you have any customers signing memorandums of understanding to lease time on the B330? And is there any federal law that would prohibit you from reaching agreements with certain governments who are interested, for example, China?
We are aware of favored nations and non-favored nations status, so we would not rub anybody's nose in that problem. Yeah, so we are conscious of foreign relationships that we need to not turn into issues. Having said that, we have actually 4 different groups today that want to fly experiments and different payloads to beam and deploy those within beam. And they've been 2 are countries and 2 are corporations. And we're hoping that maybe in half a year or something we can get permission from NASA to accommodate these people in some way. And so we have the element of substantial clientele, or us starting to collect deposits by virtue of reservations and that type of thing, has always been hostage to the availability of transportation. And we've had to throttle our own progress from different periods of time according to the ability of transportation to be there at a certain point in time. And our perception today is that we'll probably have maybe 2 systems in operation, maybe in 2018. So we can maybe make the next projection that we should have 2 structures ready for deployment, 2 B330s in 2020. Correct.
We have a couple questions up front. We'll start here and work our way to Mark.
Hi, Thaddeus Cesare with the Utica Phoenix. I was hoping to get an idea of how and if this beam technology could change the evolution and design of the International Space Station. Should we see more of these being attached?
So at this point in time, we don't envision any major changes on our NASA side or even our international partners of the actual structure of the ISS itself. We do envision at some point in the future, how do we transition from the International Space Station to commercial low Earth orbit space stations? We're trying to figure that out between us, CASIS, and commercial organizations like Bigelo, and how do we transition from an ISS-based operational model to low Earth orbit commercial space stations, where NASA is just potentially one customer of hopefully many. Does that involve going from space station to a module on station to a free flyer module? We don't know at this point. There's desires on both sides, so we'll have to figure that over the coming years.
And just as a follow-up, just hoping to hear about some of the design challenges, some of the issues in bringing this to fruition.
I think, well, I have to give a lot of credit to our success up to this point to an incredible staff that we have at our company. We also received good advice from NASA in this process. So NASA was providing insight as opposed to oversight, which is an important distinction there. So we were allowed to proceed with the architecture and the full complement of structure on our own, in concert with NASA input here and there. But I think we had a good symbiotic relationship with our team of folks and NASA people, and we're hoping if there is a follow-on project that we can maintain that same group of people and that same spirit.
Yeah, from the NASA side, technical challenges, I mean, Bigelo and his team really were the champions in this and putting the modules together. We shared a lot of our material expertise and operational expertise. Obviously, the whole lessons learned from the ISS itself. I would say that the biggest challenges were not so much the development of the structure itself, but how do you do for the first time an expansion in space? How is that dynamically going to work? How are loads and models? We don't have models for these types of structures performing. So that unknown made us do a lot of homework. And then even on the unlikely circumstances of jettison, those kind of things, the things that you hope never happen, those are the harder things to kind of answer, is how do you remove a partially expanded module and then do basically a jettison at that point of something that isn't a fully rigidized structure. So those are probably some of the challenging aspects from it, but quite frankly, most of the actual manufacturing and design and all that was all Bigelo.
All right, liftoff and the clock has started. Yes, sir, reading you loud and clear.